15 million people worldwide live with a spinal cord injury. That's 15 million people where standing and walking are no longer things that just happen. 15 million lives where moving independently is no longer taken for granted. For most of us, it is. So let me ask you this. When you go somewhere, do you ever check if you'll be able to get inside? Probably not. You simply stood up and went where you wanted to go. Now imagine waking up and discovering that your legs are still there, but they no longer respond. No feeling, no movement, no control. At that moment, everything changes. My name is Linde, and I'm the team manager of Project March 11. Today, we want to talk to you about what becomes possible when teamwork, determination, and technology come together. You might be wondering, what exactly is a spinal cord injury? A spinal cord injury means there is damage to the spinal cord that interrupts signals between the brain and the body. As a result, people lose feelings in parts of their body and are no longer able to move them. Helping people walk again will have a major physical and mental impact. If you can't stand anymore, your bones start to weaken. Bone density decreases, which means fractures are much more likely. At the same time, your heart and blood vessels don't get enough physical activity. This increases the risk of cardiovascular problems. But perhaps even more important is the mental impact of walking again. Being in a wheelchair changes even simple social interactions. Talking to someone who is standing often means the other person has to look down. Although this is rarely intentional, the difference in eye level changes how the conversation feels. It can affect confidence and the sense of equality in an interaction. And it doesn't stop there. That same difference carries over into daily life. Imagine going out with your family for a day, a museum for instance. For most of us, that sounds like an easy, spontaneous activity, right? But for some in a wheelchair, that day starts much earlier. The entire route has to be planned. Is there a step at the entrance? Is there an elevator? And does it actually work? Are there uneven floors that block the way? And can you really see the artworks the same way everyone else does, at eye level? Every outing comes with questions. And that is exactly what we as Project March want to change. Our vision at Project March is to improve the quality of lives of people with spinal cord injuries by pushing boundaries of exoskeleton technology. At the same time, we aim to raise awareness for the daily limitations and challenges people with spinal cord injuries face. Every year, a team of around 26 driven students take on this incredible challenge. For one full academic year, we dedicate ourselves to building the next generation of exoskeleton technology. We work across 5 different departments: operations, software, Embectrical, mechanical, and management. Every department plays a vital role and pushes boundaries in its own way. But it's only by working together that we turn ambition into reality. We're challenging ourselves to go further than ever before. Every year, a new team starts with fresh minds and no limits. We have already completed the analysis, conceptualization, detailed design, and production phase. We began by identifying opportunities, and from there, we defined our team goal for this year. Next, we generated countless ideas and ultimately selected the most innovative concepts. These concepts have been worked out into detail so that all components could be ordered or manufactured in-house. Now, at this design presentation, we're excited to share our new innovations and give you a preview of our exoskeleton coming in July 2026. Next week, we will assemble all components, followed by the last phase, testing and training. And that brings me to one of the most important persons of this project, our pilot. A big round of applause for Daan van der Heijden.
Good evening. My name is Daan. I'm 34 years old. And I'm one of those people around the world, one of the 15 million people that are paraplegic. For me, that happened on October 2017. For me, that means I'm from the chest down. I can't feel or move my muscles. And that's a big life event. You have to adjust from that. But luckily, by time and the necessary love, you get over that. And you can play sports, you meet someone, you do volunteer work, you meet someone you love, get two kids, buy a house, and start a family. But as a pilot, I have seen a lot at Project March. They started with a basic exoskeleton, and following by a terrain or outside scanning exoskeleton, an EEG or brain-controlled exo, and in competition, Cybertron, and other amazing exoskeletons. This is my third year as a pilot, and mostly I admire actually the students. They come in with great ideas, innovative exoskeletons, to make it within a year. And in my opinion, those students are actually the most important, not necessarily pilot. I just walk in it. The students, they take off 1 year for the study. They just pause it and to actually make an exoskeleton just in 1 year. Well, actually a school year, so 10 months. This year, 26 students. They didn't know each other before, coming from different backgrounds or different studies to make an exoskeleton. To have to be creative, young minds, all put together to make a collective. And I, as a wheelchair user, of course, I have to be creative all day. But in my house, things are different. The kitchen is a bit lower. My coffee mug is always on the lower shelf, and things I don't use, they're out of reach or end up in the attic. And my moving boxes are there for like 5 years. I didn't touch them. So that's fine. But those students, it's all in my perspective, from like in a wheelchair, but to have students behind you sometimes from, oh no, you have to get up, make an exoskeleton, and you have to start walking again. That is pretty nice. It's good to have that perspective again after 9 years. But to make an exoskeleton, there is so much happening what you don't see. Yeah, now in the design presentation, and later on we have a reveal presentation. But in that year, there is so much happening. You have an Embectrical, the electric team. They make the choice for that one chip, and I have no clue why that chip is chosen out of 1,000, but it's needed for the EXO, for the output, the power, or the safety. They chose it. Why? Don't know. And then you have the software, the walking. I know how the walking should be. It was my old profession. But to translate it in mathematics and formula, and then in computer codes, it looks amazing on a computer screen, but it makes no sense to me. And then you have the mechanical, the people that make it, the boys and girls this year actually, you have to make it in a tenth of a millimeter accuracy, otherwise it won't fit. And you have the operations, of course, and the management. So they make all these amazing presentations, animations, and everything has to be done within a budget. And that's all those things together, you don't see it, but it is happening. And you see it now, and you see it later on in the reveal, but that's all happening in 1 year. And it's thanks to these students that, and their hard dedication and the commitment, that is actually the success formula of Project March. And that's why I admire, and I really think the students are the most important. Thank you.
Thank you, Daan, for telling your story. We thank you for your incredible dedication to our project and making our visions and dreams become reality. We've talked about why Project March exists and what impact it strives to make. This vision needs to be turned into reality. But that requires a choice. What reality do we choose to create this year? My name is Koen, and I am the Chief Engineer of Project March 11. But before we answer this question with this year's design, let's take a step back and look at the fundamentals. Let's start with the fundamental working of an exoskeleton. And what better way to expand our human-centered goal to a human-centered analogy? An exoskeleton is, quite literally, an external skeleton. This means it enables posture, activity, and motion. To make these functions possible, several parts are required, just like in our own human body. The frame of the exoskeleton is the same as our bones. They provide structure and support. The mainly aluminium frame forms the foundation on which all other components are built and carries the loads during standing and walking. Next, we need movement, enabled by the joints of the exoskeleton. These can be compared to the muscles of the human body. To steer and sense the motion, we need cables and sensors, which can be compared to the nervous system of the human body. But these cables are not only part of the nervous system of the exoskeleton. They are also part of our power supply, just like the arteries and veins in the human body, which transport oxygen and nutrients throughout our body. And finally, to control movement and interpret the data, we need a computer, which is the brain of the exoskeleton. Now, with this analogy, we understand the building blocks of an exoskeleton. But to make our design, or our reality, we also need to look at the past. Let's travel through time and explore how Project March has evolved over the years. Project March was founded by a few students back in 2015. They set themselves a challenge: win the Cybathlon in 2016. In this competition, teams from all over the world compete in challenges that are comparable with daily life with their exoskeleton. By building the first exoskeleton, March 1 laid the foundations of what we are today. In the 4 years following March 1, new and ambitious teams improved and expanded the functionalities of their exoskeleton. Guided by the tests in the Cybathlon competition, every exoskeleton expanded the number of joints gradually to better resemble the movements of the muscles of the human body. From March 6 onward, the focus shifted beyond competition. The teams took their exoskeleton outside, into the real world. Walking around in Delft meant reacting dynamically to obstacles and changing surroundings. It also made balance while walking an increasingly important aspect of development. To demonstrate how far Project March had come, March 9 returned to the Cybathlon competition. The team focused on consistent and reliable performance of both the exoskeleton and its pilot, while completing the challenges in the Cybathlon competition. This goal highlights the growing maturity of the system as a whole and opened a new door for the following team. March 10 wanted to take the next step in development, to create an even bigger social impact. The team explored what it truly means to stand at eye level and engage in society. Their vision was brought to life in a setting where people gather, move, and interact closely, a concert. March 10 demonstrated that an exoskeleton can stand self-balanced, even while resisting external pushes from, for example, a crowd. As we look ahead, we want to expand what the pilot can do independently. One of the biggest challenges in achieving independence is complete balance. Most exoskeletons today require the pilot to rely on support, such as crutches, to stay upright during tasks. By focusing on balance, the hands of the pilot become truly free, regaining independence in life. March 10 pioneered self-balanced standing. Now it is time to take the next step. That's why we, as Project March 11, will build an exoskeleton that enables the pilot to visit the museum by walking self-balanced, with hands-free control, allowing natural interaction with both the exhibits and loved ones, while requiring minimal assistance to put on and take off the exoskeleton by the end of July 2026. Let's break the team go down into 3 technical pillars. Walk fully self-balanced, without the use of crutches. Be controlled completely hands-free. Require only minimal assistance to put on and take off. So, what do these pillars actually mean? And why do they matter? Imagine the pilot getting ready to visit a museum. The pilot first needs to put on the exoskeleton. Here we already see how the first technical pillar improves independence. Minimizing assistance when putting on or taking off the exoskeleton enables spontaneous participation in daily life. It allows the pilot to decide to visit a museum with family or friends, without relying on the presence of multiple helpers. This means that the exoskeleton supports daily life, rather than dictating it. Once standing, the pilot can start to walk around the museum. The exoskeleton allows the pilot to interact at eye level with both the exhibits and the people around him. For walking, most exoskeletons need additional support. I am excited to tell you that Project March 11 will show that this walk can be achieved completely self-balanced without the use of crutches. This reduces physical effort so that attention can shift from walking with the exoskeleton to fully experiencing the exhibition. Next to that, removing the crutches makes it easier to navigate through narrow pathways within the museum and lowers the risk of unintentionally touching people or exhibits. The final pillar, hands-free control, opens up an additional layer of independence. A hands-free input device ensures the pilot's hands remain fully available at all times. This allows natural interaction with both the exhibits and others, such as gesturing, pointing, holding an audio guide, or taking photographs. By removing the need to constantly hold or manage an input device, cognitive load is reduced. This creates the mental space to focus on the museum experience itself, rather than on operating the exoskeleton. Each of the pillars come together to create an experience that's more natural, independent, and meaningful for the pilot. We can imagine the pilot walking through the museum, noticing the details of an artwork, gesturing to a friend, or simply enjoying the moment without having to think about staying upright. These are the moments that define independence. They are what we strive to make possible. Earlier, we asked ourselves, what reality do we want to create? We now know what reality we want to create. But one question still remains. Exactly how will we achieve our goal? Over the past 6 months, our dedicated team has asked themselves this very important question, and we've got the answer. Now, instead of telling you what that is, we would like to show you. We are thrilled to share the design of the exoskeleton of Project March 11.
Can you believe it? Over the course of the next few months, the exoskeleton you just saw will come to life. But before we get there, let's take a dive into the technical design of this year's exoskeleton. We'll start with the large components, the mechanical design. My name is Elke, and I'm the lead mechanical engineer of Project March 11. The mechanical department is responsible for the structural aspects of the exoskeleton. The mechanical engineers develop and produce the frame and joints. Like Koen mentioned before, the frame and joints are like the bones and the muscles. They form the basis of the exoskeleton. The design engineers design the covers and make sure that all components fit together seamlessly, resulting in a fully integrated product. Finally, we have the human engineer, who makes sure that the exoskeleton is safe to operate for the pilot. This is achieved by creating reliable fixtures and maintaining close contact with Daan regarding their mental and physical health. A key step to make for independence of paraplegic patients is to allow them to enter the exoskeleton independently. That's why this year we introduce a new degree of freedom in the hip frame, the hip hinge. This hinge allows the pilot to enter the exoskeleton with ease, while requiring only minimal structural changes. So how exactly does this work? Let me walk you through the steps the pilot has to take before they can use the exoskeleton. We start our journey with the exoskeleton resting on a bench, where it was left after previous use. The pilot positions their wheelchair next to the exoskeleton and unlocks a screw on the side of the hip frame. Once this screw is removed, the hip hinge is unlocked and the pilot can move the leg outwards. This creates enough space for the pilot to safely enter from their wheelchair into the exoskeleton. After this transfer, the pilot can hinge the leg back in and close the screw again. The next step is strapping into the fixtures of the exoskeleton, which fixate the torso, upper legs, lower legs, and the feet to the exoskeleton. This year we introduce a new fixation system for the lower legs. With a simple turn of a knob, a lacing system tightens evenly around the lower legs. This ensures for reliable attachment and minimizes the risk on pressure points on the skin. After all fixtures are put on, the pilot is ready to use the exoskeleton. After use, the process is just as straightforward. The pilot sits back down on the bench, releases the fixtures, and opens the hip hinge again. They can then transfer back into their wheelchair and close the exoskeleton again. To ensure the pilot's safety in this journey, while also protecting the internal components, covers are essential in offering both aesthetics and functionality. This year, padding has been added to the covers to guide the users in intuitively removing and attaching the covers to the exoskeleton. This padding is placed in spots exposed to higher wear and tear to protect the covers and boost user-friendliness. This padding is made with a flexible yet tough core and covered with a layer of fabric, which gives it a high quality and comfortable look and feel. Apart from its functional benefits, the covers also contribute to a memorable identity, which helps us in emphasizing our message to the outside world. The message that not everything in life is self-evident, that mobility should be for everyone, and that we believe in helping people like Daan. This year marks an important milestone in that mission. This year, we will walk without crutches. The exoskeleton will move fully self-balanced, taking a major step towards true independence. To achieve this, freedom of movement is essential, and the ankle plays a key role. Imagine you're walking. Maybe the ground is a little uneven, or there's a small stone in your way. You can balance yourself effortlessly without even thinking about it. Your body is constantly making small corrections to keep you upright. And many of those small corrections you make come from your ankle. It rotates, flexes, and adapts to the ground beneath you. To achieve self-balanced walking, our exoskeleton has to replicate exactly that. Over the years, the ankle design of the exoskeleton has evolved significantly. In the early years of Project March, the foot and ankle was completely rigid. Then, in the third year of Project March, a linear joint was introduced. A linear joint is a motor that makes an up and down movement. Because this motor is attached to the heel, it allows for an up and down movement of the foot, also known as plantar and dorsal flexion. This allows for a more natural walking pattern, makes it easier to walk on slopes, and enables stair climbing. In March 9, a second degree of freedom was added to the foot, ankle rotation, also known as ankle inversion or aversion. This passive joint made use of springs to, for example, compensate for uneven surfaces. Last year, March 10 took another major step. They made the passive rotation joint active by adding a second linear joint to the foot. This allows for a more controlled balancing of the exoskeleton. Both linears now work together. When they extend equally, the foot rotates. When they move in opposite directions, the foot performs plantar or dorsal flexion, the up and down movement. Each different combination of the linear joints result in a different orientation of the foot. This year, we take it a step further. We increase the range of motion of the pilot's ankle, of the ankle of the exoskeleton, by 20%, allowing the exoskeleton to fully match the natural range of motion of the pilot's ankle. This is achieved by a complete redesign of both the linear joint and the ankle frame. The linear joint is now made 3 centimeters longer, increasing its travel. To improve precision and reliability, a new motor is built into the linear joint. This custom motor is carefully selected by analyzing data of previous years, resulting in the optimal performance for our application. In addition to this improvement, the sensors inside the linear joint are now made identical to those of the rotational joint. This makes the whole system more universal and makes it easier to integrate and maintain. Finally, a guide pin was added to prevent unwanted rotation of the linear joint. This pin ensures purely linear motion, improving both accuracy and robustness. Now, this new linear joint needs to be integrated into the ankle frame. To make sure that the ankle can make all desired movements, the ankle frame is redesigned. With help of a simulation, the optimal point of application is found of the linear joint, resulting that the ankle can fully match the natural range of motion of Daan's ankle. Tonight, I've told you all about the mechanical design of this year's exoskeleton. All these mechanical choices come together to form a basis that has the potential to move, adapt, and stay balanced. Now, the next step is to decide how or when this body needs to move.
How do we decide when the exoskeleton has to move? And how are these decisions executed? Those are the questions the software department tries to solve through code and algorithms. I'm Carlijn, a software engineer of Project March 11, and I will walk you through the biggest innovations within software this year. Fast, controlled, and precise movements of the ankles are crucial. They do not only facilitate a comfortable walking pattern, but also help with keeping balance. The improved coupled motor system, as mentioned before by Elke, helps us to easily and accurately operate these motors, resulting in the desired ankle motion. To further refine control over the system, we are simultaneously advancing our simulation model. This virtual testing environment allows us to test and train our software without directly applying it to the real exoskeleton, with the risk of damaging something. But a simulation is only as good as its accuracy. If we want to predict how, for example, the ankle will move in real life, our simulated model needs to be identical to the real life exoskeleton. So this year, we are focused on closing the sim-to-real gap. This sim-to-real gap is essentially the difference between that simulated exoskeleton and the real-life exoskeleton. Closing this gap is essential in one of our biggest breakthroughs this year, generative predictive control. But before diving deeper into that, I want to walk you through its necessity. Our goal this year is to achieve balanced walking. For most of us, walking balanced is simple. We don't even have to think about it. If we get a little push, lean to one side, or stretch out an arm, our body reacts fast and effortlessly to keep us upright. For a robot, however, nothing happens by itself. An exoskeleton doesn't have instincts. It only has the instructions we give it. To mimic that human stability, we have to replace intuition with computation. This is hard, which is why almost every exoskeleton you see nowadays still requires the pilot to lean on crutches for balance. Self-balanced walking is revolutionary in exoskeleton technology. To be able to leave those crutches behind, we need an algorithm that knows exactly where the exoskeleton is, in what position, and how to move accordingly. We need something that knows what to do when the exoskeleton gets that little push or Daan shifts his weight. We need something that reacts and does it fast. Balanced walking requires decisions to be made in a fraction of a second. And this is exactly where generative predictive control stands out. Generative predictive control, or GPC for short, is that algorithm that makes those decisions. It is essentially a control algorithm that anticipates what comes next by using generative AI. Maybe I've lost some of you here, but generative AI is something I think almost all of you have used. Think of ChatGPT or the AI that answers your searches on Google. Those are all examples of generative AI. At its core, generative AI is artificial intelligence that takes an input, for example, your question, and generates new content, the output, the answer to your question. We are applying this principle in our exoskeleton this year. But this time the input isn't a text question, but a constant stream of sensor data. And the output isn't text, but a prediction of how each joint should move next to create the desired motion. GPC makes these predictions using flow matching. It builds a vector field by training on tens of thousands of simulations, which is why the small sim-to-real gap I talked about before is so important. The vector field it builds is essentially a big map covered in arrows, giving directions. Each point on that map represents a certain position of the exoskeleton, and the arrows point in the direction where to go next. Instead of wandering through thousands of possibilities, it can follow a direct line along these arrows towards the best decision for maintaining stable. This creates a faster, more direct route towards the best decision. GPC uses this flow matching to commit to the best possible movement instantly, and like that, giving the output needed to stay upright. But it isn't as easy as saying, this is our sensor data, now walk. A computer doesn't know what walking is. We have to define it. We could define it as moving forward or tilting your feet one after the other, but then a computer may find a weird way to achieve this, with perhaps uncomfortable or unpredictable movements. We want to be able to control how we walk. We do so by designing the exact walking pattern ourselves and let GPC follow this. Following a walking pattern has been done by standard controllers before. The challenge is within keeping balance and the disturbances the software doesn't see coming. While standard controllers can follow a pattern, GPC has the intelligence to adapt. It can predict movements and adjust the motors to compensate, creating a self-balanced walk. GPC is really the cutting edge of technology. It only emerged in 2025, and Project March 11 will be the first in the world to apply it to a real-life exoskeleton. The combination of GPC and the self-defined walking pattern gives us the best of both worlds. The safety of this predefined walking gait and the adaptability of AI. But where does this perfect walking pattern come from? To be able to let Daan walk comfortably in the exoskeleton, we have to architect every millisecond of a step. We do so by designing the exact angle of each joint throughout the movement. And this year, one of the biggest innovations is that we added the computation of a certain balance point. A point on the ground where all forces of motion cancel each other out. Now, imagine the area on the ground spanned between your feet as a safe zone. As long as this balancing point stays within that safe zone, which we call the support polygon, we are balanced. This way, we can create an inherently balanced walking pattern. So, to return to the question I asked at the start, how do we decide what the exoskeleton has to do, and when? We do so by translating human instinct into code. By combining the fast responsiveness of generative predictive control with the safety of our self-defined walking patterns, we can create a system that can adapt when the exoskeleton gets that little push or Daan shifts his weight. All these innovations do not only help us to reach our goal, but more importantly, give Daan the safety and stability to take the next crutch-free step.
How do we take this step? How does the exoskeleton know exactly when and how to move each joint? How does it coordinate multiple actuators in real time while maintaining balance and stability? These are the challenges faced by our control department. My name is Daria, and this year I'm a control engineer at Project March. Our team develops the algorithms that translate position trajectories into actual joint movement, ensuring every motor delivers the right force at the right moment and in the right direction. I will walk you through how we control movement inside the exoskeleton and the innovations we are developing to tackle one of the most challenging problems in robotics, self-balanced walking. When you decide to take a step, your brain doesn't just move your leg directly. Instead, it sends an electric signal that travels down your spinal cord and across a tiny biological interface called a neuromuscular junction. Here, the signal is translated into a chemical message that tells your muscles to contract. Only then does your leg actually move. In other words, your brain sets the intention, your nervous system communicates it, and your muscles execute it. Inside the exoskeleton, the process is remarkably similar. Just like the neuromuscular junction connects the brain to the muscles, control engineers form the bridge between high-level command and physical movement. We translate an instruction into an electric signal that drives the motors. Without this translation, the joints would never know how to move. Besides direct communication with the motors, we are also responsible for the safety of the pilot. The joints may never move too fast, too strong, or in any other unexpected way. Safety is directly built into the control system through safety limits. For every joint, we define safe boundaries: how fast it may move, how much force it may apply, how far it may rotate. These limits are defined based on what is safe and comfortable for our pilot and what the structure of the exoskeleton and the motors can handle. With each command sent, the controller checks whether the resulting motion stays within these boundaries. If a command tries to exceed them, the controller will simply not allow the motion to occur. You can think of these limits like ligaments in your body. As your muscles generate force, ligaments restrict how far your joint may stretch, protecting it from damage. In the same way, the controller allows motion, but within boundaries that keep our pilot safe at all times. To communicate with the motors, we need to speak their language, electric current. But how do we know how much current to send? The idea is quite simple. Compare what we want with what we have. Our software engineers send a desired joint angle, or where we want to be. At the same time, we have special position sensors that tell us where we are. The controller constantly compares these two variables. If the joint is where it should be, no problem, the controller tells it to stay where it is. But if it's lagging behind or has gone too far, this triggers action. And the size of the difference determines the strength of the response. A small difference only needs a gentle correction, and a larger difference triggers a stronger response. Think about driving a car. A small turn of the steering wheel is enough to switch lanes on the highway. But if you want to make a U-turn, you need to turn the wheel much more. The controller does the same thing thousands of times per second. And based on the determined response, the controller sends an electric current that drives the motor to rotate. This creates a twisting force, or torque, on the joint, making it move. So far, we have been telling the exoskeleton where it has to go. If you tell it to move the knee to 30 degrees, it will do just that, no matter how hard it has to push. It does not take into account any environmental factors, such as interaction with objects or how soft or hard the ground is. A small change in the expected conditions can throw the entire trajectory off track. Another way to handle motion is to tell the exoskeleton how much force it should apply. This is known as torque control. Instead of telling it where it has to go, you tell it how hard it should push. You can compare it to your own body. Sometimes you stiffen your joints to support your weight, and other times you relax them to allow them to move smoothly. Torque control allows the exoskeleton to do the same. It offers stiffness when support is needed, and flexibility when smooth motion is more important. In short, position control tells the exoskeleton where it has to go, no matter the environment, and torque control tells it how much force it should deliver and adapts to the environment. This year, we want the best of both worlds, a combination of position and torque control to create the most optimal self-balanced exoskeleton. When the leg is in the air, we use position control. In this phase, the leg is not yet interacting with the environment and can simply follow a predefined trajectory. We know exactly where the leg should go, and we can guide it there accurately. But the moment the foot touches the ground, the physics change. Forces from the ground act on the foot and travel up through the leg. In this phase, position control is no longer ideal. That is why, as soon as ground contact is detected, we will switch to torque control. To make this possible, we have developed an algorithm that continuously monitors sensory information at each joint, such as joint angle, measured torques, and foot height. When the foot makes contact with the ground, motion slows, more forces appear in the leg, and the foot height essentially becomes zero. The controller recognizes these changes in real time and triggers a transition to torque control. We call this transition the switch. The switch is smooth and lasts for a few milliseconds, allowing the foot to land softly and absorb impact. So, position control guides the leg through the air, and torque control provides stability on the ground. And by combining accuracy in the air with robustness on the ground, we will help Daan take his next quad-3 step. A key factor that I have not mentioned yet is hardware. All the algorithms that I've described, position control, torque control, the switch, require the processing of multiple sensors simultaneously and at high speeds. Every millisecond counts for the exoskeleton's stability. This year, we require even more data, even faster processing, and even higher reliability. That is why we work in close collaboration with our electrical and embedded engineers. They make sure our algorithms not only work in theory, but can be applied in real time. So while we focus on how the exoskeleton should move, they focus on how fast and how reliably it can think.
As Daria explained how the control loop enables balanced walking, I will now show you what makes that control loop actually come to life. My name is Simon, and I'm part of the Embectrical department. If the mechanical team builds the bones and muscles of the exoskeleton, and the software team defines how it should move, then we make the nervous system that connects everything. The Embectrical department concerns itself with all electronics within the exoskeleton. Our department is a fusion between two different roles, embedded and electrical engineers. The electrical engineers produce all electrical hardware, power cables, sensor cables, and printed circuit boards. Printed circuit boards, or PCBs, are flat boards containing all types of small electrical components. We assemble these boards in-house by soldering the components onto the boards ourselves. We design our own PCBs to maximize efficiency and minimize size. Each connection is precisely engineered to ensure our hardware performs reliably under real-time conditions. But hardware alone does nothing. Just like your computer needs software to function, these boards require an operating system to run, which we call firmware. This is necessary for all the components to communicate as expected with the main computer and the sensors within the exoskeleton. This is where our embedded engineers come in. They concern themselves with designing and developing firmware for these boards. As a whole, the Embectrical department forms the interface between the mechanical behavior of the exoskeleton and the high-level software running on the computer. As Daria explained earlier, the joints are controlled using a control loop. The M drive brings the control loop to life. It connects the software to our motors by generating an electrical signal and sending it to the motors such that the joints move. Each M drive has the capability to drive 2 motors. Since we have 10 joints, there are 5 M drives present within the exoskeleton. They are located in both of the upper and lower legs, and we have one in the backpack. However, controlling movement requires more than just sending signals. To know what signal we have to send to the motors, we first need to know the current state of the joint. At what angle is it? What torque is on it? For this, we rely on sensors. Each joint contains an encoder, which determines its angle. Additionally, each joint contains a torque sensor. This data is important for the control loop. With the goal of this year being self-balanced walking, the computational demands have increased significantly. We are processing more sensor data than ever before, and we have to do so faster and more reliably. This is why we have upgraded the M-Drive's processor. Previously, we used the STM32F4, but this year we are transitioning to the STM32F7. This upgrade increases our clock speed by 30% and expands available RAM by 70%. To put these specifications into perspective, imagine the processor as a mechanical engineer tasked with the assembly of a joint. By increasing the clock speed, the mechanical engineer increases their speed of twisting nuts and bolts into place. With an increased RAM, the mechanical engineer expands their workspace, leaving more space for various tools. This way, the engineer can easily access the right wrench for the job, increasing the efficiency of completing the task at hand. However, balanced walking isn't just about hardware and computation, it is also about user experience. The input device allows the pilot to select walking modes, such as standing or walking. In previous years, the input device was usually embedded into the crutch of the pilot. However, with balanced walking, crutches are no longer needed, which gave us the opportunity to completely redesign the interaction experience. This year, we have developed a new input device, located near the right hip of the pilot. The pilot can use it either holstered or handheld, depending on the situation. The device slots into its holder upside down, such that the screen remains correctly oriented for the user. It is secured using magnets, making it both stable during use and easy to detach when needed. To elevate the hands-free experience even further, the input device is connected wirelessly to the exoskeleton. It communicates via Bluetooth for a stable and reliable wireless connection. At the same time, we implement the ability to work wired as well. If the battery were to run out, simply plug in the device with USB-C to the exoskeleton such that it can be used in a wired manner. Safety is a key priority. For that reason, we integrated an inertial measurement unit, which measures the acceleration on the device. If the device were to fall to the ground, the exoskeleton would otherwise continue walking, while the pilot could no longer send a command to switch to stand mode. To prevent this, the system automatically switches to stand mode when a large acceleration is detected. In this way, a potentially dangerous situation is immediately avoided. The input device already makes the experience significantly more hands-free, but we asked ourselves, can we take this even further? What if the pilot didn't need to press anything at all? To let the pilot control the exoskeleton completely hands-free, we have developed a system which detects the pilot's intention for walking from brain signals using EEG technology. This is a technology which measures brain activity through electrodes placed in a cap on the head. By focusing on how the legs would move when walking, specific brain signals can be detected. The pilot's intention for walking can be decoded from these signals using machine learning. The intention is sent to the exoskeleton, which allows the pilot to either walk or stop the exoskeleton's movement. This year's EEG results mark a true breakthrough for us. After 4 years of research, we have achieved a working model which connects brain signals to real steps. Using this technology, the pilot can regain his ability to walk naturally, without the touch of a button. And with that, we take one step closer to restoring walking in the most natural way possible.
At the beginning of this design presentation, we told you about the daily limitations people with spinal cord injuries face. Today, we have shared with you our ambitious goals for this year. We, as Project March 11, will build an exoskeleton that will enable our pilot to visit the museum walking self-balanced with hands-free control. An exoskeleton that allows natural interactions with both the exhibits and loved ones. One that requires minimal assistance to put on and take off. And we will achieve this by the end of July 2026. We do this with one clear purpose: to improve the quality of life of people with spinal cord injuries, so that Daan can stand again, walk again, and move through the world independently. None of this would have been possible without the support of our partners. As a non-profit organization, we're fully dependent on your support. So thank you for all that made this project possible. None of this would have been possible without the previous years of Project March. Thank you for the foundation that you built. And thank you for all the coffee breaks where we brainstormed, asked thousands of questions, and kept faith in this project. We would also like to thank our friends, family, and loved ones. Thank you for your patience, support, and belief. Speaking on behalf of the entire team, we're incredibly proud of what we put up here tonight. This is the result of thousands of hours of hard work from all departments. Therefore, I would like to ask for a big round of applause for all departments, beginning with the mechanical department with Elke, Amy, Britt, Duncan, Tijmen, Tom, and Boran. The software departments with Mark, Lucia, Carlijn, Jane, Doris, Lies, Daria, and Max. The Embectrical department with Rongjin, Bart, Aljin, and Simon. The Operations Department with Bente, Okke, and Laila. And the management with Imelda, Koen, Roos, and me, Linde. Last but not least, a big round of applause for our pilot, Daan. Thank you all for coming. We would like to invite you again to our review presentation in July, where our pilots will give a live demonstration of our fully completed exoskeleton. For now, we would like to invite you to the foyer and have a drink with us, where you can also see our previous exoskeletons. Thank you all for coming.